No? Okay. Okay, so number two, you have a rigid tank with a volume of 1.5 cubic meters, and it's filled with steam. And initially, you have a pressure at instant 1 of 5.0 bar and a temperature 1 at 240 degrees Celsius. And then this process happens where there's a constant mass flow rate. So we can think of ME dot is equal to 0.2. And we have to figure out the initial mass in the tank. That's part A. Second is the time at which um, 67.825% of the mass is leaked out. So in other words, we can think of that as M2 is equal to 0.32175 M1. A lot of people, you're sort of rushing on a test or whatever. It wasn't a big deal to me. If I took off, so a lot of people said M2 is 0.67825 times M1. And if you did that, I hope I didn't take off any points. I know I didn't for most people. If I did take off points for that, come show me and I'll give it back. But it did make your job harder because if you did it the way I meant for you to do it, then there was no interpolation. You have to be very lucky for that to happen. So if you did it the other way, you probably had to interpolate then. And then the last thing we want to calculate is the pressure at time 2. Okay, so for part A, I'm just going to go through this whole thing. You know the pressure and the temperature. So you know P1 and T1. And so you can just look this up in a table. And the table gives you that the specific volume at instant 1 is 0.4646 cubic meters per kilogram. And you know the total volume. So volume 1 is equal to M1 times specific volume 1. So 0.4646. Let me put it this way. To get M by itself, M1 is equal to 1.5 cubic meters divided by 0.4646 meters cubed per kilogram, and that gives you 3.229 kilograms. And then second, we want to know how long it takes for 67 point whatever percent to leak out. So we're going to use conservation of mass. And that says that the rate of change of mass inside the control volume is equal to the mass in dot minus the mass out dot. The only thing that's happening in this problem is that mass is leaking out. So this is 0. And so dm dt for the control volume is just equal to negative 0.2. We know that, there's a couple of ways to think about this integration. One is we know that the mass at instant 2 is 0.32175 times the original mass, and that gives you 1.039. And so if you take this differential equation, you can integrate both sides, and the integral of, let's say, dm cv is equal to the integral of negative 0.2 dt. Now we have to think about the boundaries. The time, we're just going to go from 0 time, we're going to call state 1 times 0. So 0 to t, and the t in the integral, the dt is just a dummy variable. For the mass, we're going to start at 3.229. That's the mass at state 1. And at state 2, we now know we're going to be at 1.039. And so 1.039 minus 3.229 is equal to negative 0.2 t. And so t is equal to 10.95 seconds. And then the last part, we're trying to figure out the pressure at this time. Well, we still know the volume because it's a fixed tank. And so the volume at state 2 is still equal to 1.5. Gas just expands. That's the fart rule. The gas just expands to fill the whole tank. So even though there's a lot less of that steam in there, it still has that original volume. And so 1.5 is equal to the new mass, which is 1.039, times the specific volume at state 2. And we can use that to calculate the specific volume. And you get a specific volume of 1.444 what are the odds that that would actually be a value that's right in the table? That would be amazing. But it is. So that's a specific volume value in the table. And so then you can sort of do a reverse lookup of the pressure, the temperature. Let's see. Yeah, that T2 is 200 degrees Celsius. V2 is 1.444. And so you can use the table and just find the pressure that has that value, and you get that pressure is 1.5 bar. Any questions about that? Anything on that problem? Yep. That is, so it says that you're losing 67.825% of the mass. And so what's left is 32.175% of the original mass. It's just like 1 minus that. And so I just chalk that up to, people like sort of rushing to get done with problems on a test. And so I didn't take off points for people who thought of that second mass as 0.67825 times this. Right. Yes, exactly. Same thing. Yep. Any other questions? Okay. Anybody have any homework questions? I guess I didn't give any homework. Did I? When did we take this test? Thursday? Oh, Tuesday, a week. All right. Well, so let's go back to what we're talking about. So we're going back to the second law of thermodynamics. And there wasn't much that we did with the Clausius statement of the second law. But you can prove that the Clausius statement is equivalent to the Kelvin-Planck statement. And that opens up a little more kind of mathematical power. So the Kelvin-Planck statement is used in a lot of the proofs later on. And the Kelvin-Planck statement is the one that we're going to eventually turn into the entropy statement. So the Kelvin-Planck statement is equivalent to the Clausius inequality. And then the Clausius inequality is going to give us the entropy statement. We've pretty much said all we're going to say about the Clausius statement of the second law. We're on this one right now. And we just started talking about performance of cycles. And one of the uses of the Kelvin-Planck statement is coming up with not just definitions of performance of these cycles, that doesn't depend on the Kelvin-Planck statement, but coming up with, for the conditions that you have, really it's for the temperatures of the two reservoirs that you have for your cycle, coming up with limits on the performance of the cycle. So it turns out that if you have a heat engine with a boiler of 500 Kelvin and a condenser, the cold reservoir of 200 Kelvin, there's a theoretical limit. If you have no irreversibilities in your system, there's still a finite limit on the performance of the power cycle that you can get out of that, or the refrigeration cycle, or the heat pump cycle. So that's what we're doing now. We're sort of working towards that. And I just started talking about performance of cycles. First, the only one that I brought up before is the power cycle. And in a power cycle, you have a hot reservoir here, a cold reservoir here. So for a power cycle, what's the heat transfer between the system in the middle and the hot reservoir? Which direction does it go? Okay, so you have QH going that way. And what about QC? Which way does it go? Yep. And then what do we know about the work? What happens with work? Yeah, we're using the power cycle to produce work. So that's the direction of all those changes in energy. And if you could define a perfect power cycle, what would it have a lot of? So our efficiency is, I mean, just what do you want the most from a power cycle? You want work is what I'm trying to get at. Yeah. So this is the efficiency eta, and it's equal to the work. You want a lot of that, and what do you want a little of? What do you want to minimize as much as possible? The cost of running this engine is the heat you have to put into it. You know, the coal to keep the fire running, or the whatever, the nuclear reaction in modern heat engines. So it's work over QH. And since this is a cycle, the energy inside the system, beginning and end of the cycle, has to be the same. And so that means that the flow in has to equal the flow out. So QH has to be equal to the work plus QC. And so if you rearrange that, work is equal to QH minus QC. That lets you rewrite this in a case where rewrite it in terms of the heat gained and the heat lost as QH minus QC over QH. That gives you 1 minus QC over QH. We'll see pretty soon why that's a useful form of this, but it's excuse me, it's just rearranging this relationship that we have to have because this is a cycle. Okay, it's a cycle, so this just has to be the case. Okay, that's the efficiency. So now let's go to a refrigeration cycle and think through this the same way. So here's the system. Here's the hot reservoir on top and the cold on the bottom again. Now, for refrigeration cycle, let's think about the directions of the energy transfers. So first, what's the direction of energy transfer, of heat transfer between the hot reservoir and the system? Well, refrigeration cycle, I think a better way to think of it is, well, so where do you put the vegetables in the refrigerator in this system? And so what we're trying to do is pull heat out of the cold reservoir, pull heat away from the vegetables to make them colder. And so the heat transfer goes from the cold reservoir to the system. So QC is this direction. We want to deposit that energy out in the environment, out in the room. It has a higher temperature than the cold reservoir. So QH is like this. And what about work? Work has to be done. That's the compressor in a refrigerator. That's the way that you manage to move, the Clausius statement. So what does the Clausius statement have to say about a refrigeration cycle? At first, it sort of looks like the Clausius statement says you can't have a refrigeration cycle because you're taking heat from a cold reservoir and moving it to a hot reservoir. That's exactly what the Clausius statement says doesn't happen. But the Clausius statement says it doesn't happen spontaneously. It can happen non-spontaneously. Is that a word? It can happen if you do other stuff to make it possible. In the case of refrigeration cycle, you use a compressor to compress the refrigerant, raise it to a higher temperature, then hold that up to the coils in the back of the refrigerator. Heat energy goes out, then you let it expand again, and the temperature goes back below the temperature it was at before. That's how it works. So in this case, we don't talk about it as efficiency because in this case, you can get a value higher than 1. We talk about it as the coefficient of performance, but it's the same idea. So we'll call this one uppercase Greek letter beta. And again, it's just going to be a ratio of the thing that we want divided by the thing we want as low as possible. What's the thing that we want to happen the most? The whole goal of a refrigeration cycle is a large what? QC. And what's the thing that we put into this as is work? Yep. So here's the coefficient of performance. And again, we're going to write this all in terms of heat, and I'll show you why when we get to the theoretical limits on the coefficients of performance of these different things. You'll see why that's useful. Okay, again, now, this is a cycle. And since it's a cycle, there can't be any changes in energy in the system. At the end of one cycle, the energy has to be the same as it was before the cycle, the same after the next cycle. All of the directions of these things change. So we have to sort of think it through again. All we're doing again is saying that the sum of the energy transfers into the system have to equal the sum of the energy transfers out of the system. But since everything's just reversed, it looks the same as it was before. I'll write it in the opposite order this time. So before I said the energy in is equal to the energy out. So this time the energy in is QC plus W, and that's equal to the energy out. And again, I'll isolate the work, and so you get the work is equal to QH minus QC. And so you can rewrite this substitute in for work, and you get QC over QH minus QC. One thing to notice about these is the limit on the so the biggest coefficient of performance you can have for a power cycle is 1. Can't get any bigger than that. But you can get bigger than 1 for the coefficient of performance for a refrigeration cycle, or we're going to see for a heat pump cycle. Like imagine a case where well, it'll actually not more obvious from this, but we'll see it when we go to the theoretical limits. Anybody have any questions about this yet? Yes. That's perfect. But we're going to see that even for a power cycle with no irreversibilities, so like frictionless and everything's at perfect efficiency, there's a limit to the efficiency you can get, just depending on what your boiler temperature is and your condenser temperature is. So that's what we're going to see, and it's sort of a surprising result, but we're going to see that. Any other questions? Okay, and now the heat pump cycle. So here's the system. Here's the hot reservoir. Here's the cold reservoir. What are the directions of QC, QH, and W in this one? So let's first think about what do you want a heat pump to do? If you didn't have any of the other stuff, there's only one thing that only has one job, and its job is putting heat energy from the system to the hot reservoir. Okay, the hot reservoir is where you're sitting inside your motorhome. Okay. So QH goes that way. Well, okay, it needs to get that heat from somewhere, and so it needs to take heat energy from the cooled reservoir. So QC goes into the system, and these are going the same direction as the refrigeration cycle. So which way does work have to go? Yep. And the main thing to remember, the relationship between the refrigeration cycle and the heat pump cycle, is if you look at the two, it's exactly the same cycle. It's just a matter of which reservoir is the important one. you put your vegetables in the cold reservoir, you put your people sitting in the hot reservoir, and in that case, it's working as a heat pump and a refrigeration cycle at the same time. Okay. Well, if everything's working the same as the refrigeration cycle, then this relationship still has to be the same. Plus QC is equal to QH because it's a cycle. And you can see that from the diagram. And now we want to think about what it means to define the performance. Well, at first thought, you might think defining the performance of a heat pump would be exactly the same as defining it for a refrigeration cycle. But we have, because they work the same, but we have different goals for these two cycles. So it makes sense that you'd have a different ratio of things for the coefficient of performance. This we're going to call the Greek letter gamma, I believe. Yes, gamma. And what is the one goal of a heat pump? Right. So QH. And what's the cost of running a heat pump? Work. So from up here, we know the work again is equal to QH minus QC because it's a cycle. And so we can substitute that in and we get QH over quantity QH minus QC. Okay, so right now, if you were able to calculate the heat transfer at the different reservoirs into the system, out of the system, you could calculate how, basically efficient. You can calculate how well this thing is functioning for what you want it to do. But now we're going to start thinking about the performance of, so what can we say let's say perfect performance. And we're going to call this perfect performance. So that is the performance of a system with no irreversibilities. Nope, it's not going to. Well, so, I guess in a way, you should think of it as like it depends how you define perfect. If you look at the heat pump cycle, if you define perfect as that one won't do it. Well, yeah, I guess in this case, if you define perfect as getting work out of this thing and you don't have to put any energy into it, that's perfect in some sense, but we already know that's impossible just from conservation of energy. The next one, well, what if you could transfer heat to the cold reservoir and you didn't have to do work? Well, we know that's impossible, not from conservation of energy, but now we know that's impossible from the second law of thermodynamics because that violates the Clausius statement of the second law. But what we're heading towards is, so each one of these is kind of giving us uh, a more useful, more strict uh, definition of the maximum allowable that you can expect from this thing, you know. And we're heading towards one that's more strict than just saying that the work has to be something. We're going to actually see uh, finite numerical values for, okay, so what if you had this perfect thing? There was no friction. All of the heat transfer happened in a way where you didn't lose energy. Um, there were no chemical reactions, none of that stuff that makes systems irreversible. Could you get perfect performance? It turns out no, and that's what we're heading towards. Okay. What can we say about perfect performance? That is the performance of a system with no irreversibilities. Um, so that's where we're heading now. And the first step towards getting there is, well, let's compare cycles by different kinds of totally reversible systems. Um, so the first step is there are going to be two important corollaries to the Kelvin-Planck statement. So the first one is, well, okay, if we're calling, so if we're saying a perfect system is one with no irreversibilities, how do you, like, what do we do with, like, say we have one really good, well-designed, um, totally reversible cycle here, and then a really badly designed reversible cycle here. You know what I mean? So what about the performance of those two? And are we talking about the performance of the better one or the worse one, that kind of thing? Okay. It turns out, and again, I'm not going to go into the proof, but you can, these proofs are all like a page or less in a textbook. The first one is that no matter how you design a reversible cycle, power cycle, refrigeration cycle, the performance is the same. So just getting out all of those, all of the friction, all of the lost energy due to inefficient heat transfer, all that kind of stuff. If you do that, no matter how you design your power cycle, you get the same efficiency. Okay. So that's the first one. All reversible power cycles and this is also true of refrigeration cycles and heat pump cycles. Um, operating between the same two thermal reservoirs um, have the same performance. It's a little surprising. If you want to try to sort of make sense out of an analogy that, like how to sort of wrap your head around it, I think, imagine a totally frictionless system where you're going to take a block and move it from this spot to this spot. Okay. So first, imagine that that block, let's say it has some tiny infinitesimal speed or whatever, and you just have a flat line, a flat surface between these two spots. It'll eventually slide there, right? And you can, so now you can imagine how that would work, and it doesn't take any energy to go from here to here. Okay, it doesn't, you don't have to apply a force to it or anything. Okay, now imagine that surface is gone, but now you have a hill that drops down 6 miles and then comes back up 6 miles to the same spot. Okay, that's a long way for this block to travel. But if you start it with that same initial infinitesimal velocity, remember, we're assuming no irreversibility, so there's absolutely no friction. It's not realistic. But this block will slide all the way down, pick up speed, bottom at a fastest speed, slide all the way back up, and it will get to that spot. So which of those two is, practically speaking, a more effective way to get a block from here to here? Well, in any realistic system, it's way easier to just slide it along the flat line. But you take out some of those practical considerations go away when you remove the irreversibilities, when you remove the friction. And so even though clearly by anybody's account, it's a better designed system to have it slide this way, if you're talking about fully reversible systems, no friction, you can take whatever path you want and it'll get there. Okay, that's sort of what's going on here. If you make it unrealistic, take out any sources of irreversibility, it doesn't matter how you go about it. When you get there, you won't have wasted any energy. That's the idea. Yes. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Yeah. Yeah. Irreversibilities. Yeah. Right. Right. Well, no. I mean, well, uh, no. Those are two separate things. Those are two separate things, and both are a problem. Like there are people trying to optimize both of those two. Although I suppose in a lot there's some cases where the irreversibilities are leading to the damage that breaks it. So like if you have fluid flow, you have friction in the fluid flow. That's putting extra stress on the joints of the heart or whatever. But yeah, think of those as two separate things. So we're just talking about the energy loss. And you could imagine a world where this thing was just so robust. I mean, if you made an artificial heart that was made out of stainless steel and the walls were this thick, like it would last forever, but you'd still have to worry about the energy losses and stuff. And your chest would look sort of awkward. Okay, so yes. Yes. Well, oh, I see what you mean. No, any chemical reaction is an irreversibility because you can't. So the word irreversibility comes from the idea that you could say like, okay, everything back to where it came from, and without changing anything, you could send it back. Well, that's not how chemical reactions work. They have a preferred, you know, if you if you put a lot of oxygen atoms in a room, they immediately form O2. And now you're like, okay, separate again. And they're like, no. Yeah, exactly. So that's an irreversibility and it causes energy loss. Well, now that we know that any reversible system has the same performance, this second one probably isn't too surprising, but it's an important. Yeah, I mean, you would probably make this assumption on your own, but this has to be true for the thought process that we're going to follow, and that is that also any cycle with irreversibilities has worse performance, lower coefficient of performance. So second corollary is that, well, let me say all again. So all power cycles, and this is also true of refrigeration cycles, heat pump cycles, with irreversibilities have worse performance than all those reversible cycles. That makes sense, right? The second one makes sense. I mean, you would have believed like if there were different reversible cycles that had different performances, you could believe maybe with a tiny amount of friction in the better designed reversible cycle, you could have better performance than a worse designed reversible cycle. But since now we know they're all the same, like, sure, that's obvious. All right, well, before um, before we use this for mathematical relationships, I just want to bring up, and we're not going to do calculations with this, but I just want to bring up what's probably the most well-known, well-studied reversible power cycle. That's called the Carnot cycle. You might have heard that in passing in physics, end of physics 1 or beginning of physics 2. This is an aside, but this is just like a word you should know. So this is a reversible power cycle. And if you run it in reverse, it's reversible, so everything works just as efficiently if you run everything backwards. So it's also a refrigeration cycle or a heat pump cycle. If you run it in reverse. And the reason that people study this one is is, so why would we bother studying this? Well, the first reason is that it's a relatively easy reversible cycle to analyze. And then is, maybe this is sort of implied by the thought process I've been following, but well, we only have to be able to do calculations for one type of reversible cycle because they're all the same. Um, so since all reversible cycles have the same performance, we only need to analyze one. Okay, so here is how this system works. So this is a Carnot power cycle. We're going to think of it as a cylinder piston system, and we're going to have, so state 1 to state 2 to state 3 to state 4, and then back to state 1. And here's what it looks like. So state 1 is going to be, so there's the piston and the cylinder. Here's the system inside there. At state 1, it's half full. At state 2, it's all the way compressed as much as it can be. At state 3, it is, let's see, one, two, three. At state 3, it's now expanded, so it's halfway full. At state 4, it's continued to expand, so it's all the way full. I say full, it's the same amount of material, but we're just talking about the amount of volume. And then state 1, it's returned to halfway. Okay, so this is half, full volume, half. This is minimum volume. And state 1 is half. Okay, so the first step, this is process 1. I'll say process 1 to 2. And that is an adiabatic compression. Anyone remember what adiabatic means? Adiabatic means no heat transfer, so it's insulated or very fast. That adiabatic compression is followed by, so this next process from states 2 to 3 is an isothermal expansion. Anyone remember what isothermal means? Constant temperature through this expansion. That isothermal expansion is now followed by an adiabatic expansion. So the idea is here for that process from state 2 to state 3, the system is in contact with the hot reservoir, the high temperature reservoir, and it's expanding. Then you shut off that contact with the high temperature reservoir, and the process from state 3 to 4 is an adiabatic expansion. And then returning to the starting state, process 4 to 1 is an isothermal compression. So so if you think about like contact with different reservoirs, the process from state 1 to state 2 is adiabatic, so that's insulated. The expansion, the isothermal expansion from state 2 to state 3 happens because the system is in contact with the hot reservoir. Then the adiabatic expansion means that it's insulated again, so not in contact with either reservoir. And then finally, the isothermal compression, that's contact with the cold reservoir. Okay, so that the Carnot efficiency, Carnot engine, Carnot cycle, that's just, Carnot is just, well, it was the name of a thermodynamicist, and it's just a name that you should recognize, and this is what it means: a very specific set of processes that form a reversible heat engine or reversible power cycle. And you can run it exactly in the backwards order to make a refrigeration cycle or a heat pump cycle. Yes? Well, it's describing a mathematical model, but people make physical versions of it where they minimize friction as much as they can and make the heat transfer with a hot reservoir and cold reservoir. As like, notice that isothermal expansion. Remember that I said one of the sources of irreversibilities is heat moving through a finite temperature difference. you remember that? Um, so if you have a gas that's at 70 degrees and you put it in contact with a thermal reservoir that's at 80 degrees, that's a finite temperature difference. And the whole time that heat is being transferred from the reservoir to the 70-degree system, that system's temperature is increasing, right? The fact that we have these two isothermal expansions and compressions when the thing's in contact with the reservoirs means that that's an infinitesimal temperature difference. And so how long does it take for any finite amount of heat transfer to happen over an infinitesimal temperature difference? What would you guess? An infinite amount of time, so you can't do this exact, so like this room's at 70 degrees. Okay. Say that we made that wall copper so it conducted heat pretty efficiently. And outside, we made the temperature of the air 70.000001 degrees. Okay. That's still a finite temperature difference, but okay, we'll say that that's infinitesimal. Okay. How long would you guess it would take for 1,000 kilojoules of energy to transfer in here through heat? A ton of time, because that's just such a small temperature difference. And that's the problem that you're facing with making a truly reversible cycle. But anyways, people do make models where they approximate this stuff, and you can get pretty good efficiency and get pretty close to the theoretical limits. But I don't know of any. Maybe this is also part of your question, is like, I don't know of any practical. I don't think that there was ever like a moped company that used a simulation of a Carnot engine or anything like that, Any other questions about that? Okay, well, yeah, let's stop there. And next time, so I still can't give you any new problems. I can only give you old problems. It is Thanksgiving, I guess. And next time, we'll finally get into some equations and being able to do some problems.